All right, so in this next video here, we're going to continue to look at solving exponential equations, but here we're going to run into a couple of bumps in the road that we've got to deal with. So in example 4, we look at this and we see we've got variables in the exponents on both sides of the equation. And then we also have this 4 out here that is kind of problematic, and the reason it's problematic is because we know that one of our goals is to get the exponential all by itself. However, that's not possible here, right? So if I divided by 4 on the left, then that would just put a divided by 4 on the right. So then this one would be by itself, but this one wouldn't. So in this case, we cannot isolate our exponential because we have two different ones. So at this point, we might say, well, is there any way that we can go ahead and just take the natural log of both sides anyway? And we don't really have much else to go on, so let's go ahead and do that. So we'll take the natural log of 4 times 2 to the 3x minus 7 equals the natural log of 3 to the x. All right, now what we have to do at this point is think carefully about what our laws of logarithms say and what they don't say. So the power rule for logarithms that we've been using to solve these problems has been this, right? If you have something that looks like this, you can bring the exponent down in front, and that's what allowed us to untrap the variable from the exponent. Okay, but if you look carefully here, you can apply that without much trouble to the right side, right? You can bring that x down and that looks fine. The capital A is my 3, right? X is my r, works fine. But in this case, it's more tricky because this 4 is not being raised to the 3x minus 7. And here, it doesn't say anything about what to do if you have another number in here. So this property, as it's written, cannot be used on the left side. But here's where we want to remember that this was not the only law of logarithms, right? We also had this one. If I have the product of two things inside the argument of the logarithm, I can turn this into the log base b of a plus the log base b of c. Right? I can turn it into this. And this is going to be important because if I use this property right here, then I can write it as the natural log of 4 plus the natural log of 2 to the 3x minus 7. And now, when I look at the 2 to the 3x minus 7, now there's no other coefficient in front that's not being raised to the 3x minus 7. Now all I have here is this base that you see here. And so now I am allowed to bring it down front. So we have the natural log of 4 plus, now I bring this down, 3x minus 7 times the natural log of 2. And then of course we can do the same thing on the right side here. Okay, so that's where we're at now. At this point, it's kind of a big mess, though, right? And you might struggle to figure out what your next step is. So here's a little trick. If you are ever at a point in your equation and it's getting pretty ugly and you're struggling to figure out what the next step is, over on the side, I want you to make yourself a fake problem. Okay? And your fake problem should look a lot like what you have, except for drop all those natural logs out of it, because they're the things that are really cluttering it up. So let's suppose that your equation was this: 4 plus 3x minus 7. And instead of natural log of 2, let's just say there's a 2 out here. And x times, well, I'm going to put the 3 first, 3 times x. Okay, very similar to what I have, but I took away all the natural logs. And if you ask yourself, okay, what would I do next in this problem? I think that we would all realize, oh yeah, I want to go ahead and distribute that 2 through so that I can untrap the x from parentheses, right? So you would say something like 4 plus 6x minus 14 equals 3x, right? Okay, so if that's your answer for what to do in this simpler looking problem, then that's also your answer for the real problem. So you're going to go ahead and distribute this through to both of those terms. So you'll have the natural log of 4 plus 3x natural log of 2, right? There's no pretty way to combine your 3 and your natural log 2. Well, I guess there is, but it's not worth doing. It might be more confusing than it's worth. So just write it out. So 7 times the natural log of 2 equals this. All right, so 1 second here. This doesn't look very good, does it? There. All right, so then what do you do next? Okay, and it's quite natural to get stuck again here because, again, this is not the nicest thing to look at. Okay, so let's go back over to our yellow problem. In the yellow one, what would I do next? Well, I'd probably get all the x's on the same side, right? So I might subtract my 6x from both sides. Okay, and once I determine that, I come back over here and say, well, what's the equivalent of my 6x? Ah, it's this one. So yeah, let's get our x's all on the same side. Oops, forgot my 3 there, sorry. All right, so we end up with the natural log of 4 minus 7 natural log of 2 equals x natural log of 3 minus 3x natural log of 2. Now, in the yellow version, we're pretty lucky here because you can just combine like terms, right? So you end up with, negative 3x on the right, 4 minus 14, so negative 10 on the left. Okay, so that doesn't really matter where we're at here. The point is this last step is something that I'm able to do because these numbers are so nice, but I can't quite do it here. So the equivalent of combining like terms when things are just not nice enough to combine easily, the equivalent of that is to factor an x out of both terms. Right, and this is the type of thing you had to do back when you were working with inverses, right? There were certain inverse problems when you would solve for those. You had to then factor out the variable from more than one term. And as bad as this looks right now, don't forget that this is a number. This is a number. So if you have a number equals x times a number, just like I do here, we know over here we just divide by negative 3, right? So now we're just going to divide by what's next to the x. So divide by the natural log of 3 minus 3 natural log 2. Okay, and so just to clean up what we've got here, this will be x equals the natural log of 4, natural log of 4 minus 7 times the natural log of 2, natural log of 3 minus 3 natural log of 2. All right, now one of the hard parts of these problems is that depending upon how you decide to go about the problem, your final answer might look quite different. And so what I have here, this is my exact answer, right, as we talked about earlier. So this is a really good type of problem to make sure you also get the approximate answer. Especially, like I think I've said this before, but if you're comparing your answer to my answer, for example, if we choose to go about things a little bit differently in all this process, we very well may both have the correct answer, but they're just going to look different. So let's type that in our calculator. Now, I want to just take a moment to make sure that we discuss this carefully, because you do have to be careful when you type this kind of stuff in. So everything on top of the fraction has to be in parentheses, and everything on bottom of the fraction has to be in parentheses in order for the order of operations to be interpreted correctly on your calculator. So that becomes difficult when every time you type in a natural log, it's got its own little set of parentheses. So you got to really count up your parentheses pretty carefully. So notice I've got the parentheses around the 4, the parentheses around the 2, so I need another one to close off the top of the fraction. Then I can hit divide, and then I'll put my parentheses, and then natural log of 3 minus 3 natural log of 2. And I close my parentheses again. So you just got to, take an extra second, make sure you got it in accurately. So I get 3.53 when I do that. Okay. And you'll see, on one like this, you really do have to take the log of both sides. Rewriting it in its logarithmic form just wouldn't work. It's too complicated when you've got variables on both sides, each in their own exponent. All right, this would be a good one for you to try before you take a look at my solution. So give it a try first. See how you're doing with these types of problems. All right, so I see that I can't do anything to make it so that both exponentials are isolated. So if I can't do that, then I'm not too bothered by the fact that I have a number on both sides that isn't a part of the base. So the way I would elect to do it is just to go ahead and immediately take the natural log of both sides. Okay, so before using the power rule, we break it up with the multiplication to logarithm addition rule. And then I can pull these exponents down. So we'll have the natural log of 2 plus x times the natural log of 1.7 equals natural log of 9 plus 2x times the natural log of 3.2. Okay, and so as we've done in the past, we want x's on one side, stuff without x's on the other. So I should do this subtraction, and I can also subtract the natural log of 9 from both sides. So I'll end up with the natural log of 2 minus the natural log of 9. And then we have 2x natural log of 3.2 minus x times the natural log of 1.7. And we've got an x in both terms. I want just a single x, but because it's common to both of those terms, I can pull it out. So x times 2 natural log 3.2 minus the natural log of 1.7. And again, it's just a number equals x times a number, so we divide. So just to clean up here, here's our final exact answer. But let's go ahead and put that in our calculator. When I do, being really careful with my parentheses, I should get negative 0.84. All right, now what I want to do in this example is go back to a topic we've already discussed, which is investing money in an account that earns compound interest. So it says, suppose you invest some amount of money in an account that pays 5% annual interest. How much time does it take for the investment to double when the compounding is quarterly? What if the investment compounds monthly? Okay, so they've asked us to answer this question. Let's take it one at a time here. So quarterly. All right, so we're making an investment. We know that 5% is the annual percentage rate. They don't tell me how much I'm investing. They're just asking how long it takes to double. All right, so remember our general equation here is A of t is equal to A times 1 plus R over K to the KT. So we know R is 0.05, and I guess we know K is 4, right? Because we're talking quarterly. But that's all we know. But because they're talking about the investment doubling, I don't really need to know what A is, right? So if you invest $8 into this account, then doubling it would just mean at the end you have twice what A is. And so this is why, of course, it doesn't matter that we don't know what A is, because they just cancel from both sides. So we're left with this. 2 equals 1 plus 0.05 over 4 to the 4t. All right. So what do we do now? Well, we have this exponential expression. And so let's do what we've been doing. Let's take the log of both sides. So if I take the log of the left and I take the log of the right, we remember that our whole purpose in doing this is so that we can get the variable out of the exponent. And even though this base is really kind of complicated, I can definitely take that base raised, or that base is raised to the 4t. So all of this is raised to the 4t. So I can use my power rule. So I have 4t natural log 1 plus 0.05 over 4. Okay. Now I know that this kind of looks a little bit tough, but this is a number times a variable times another number. Okay. Now, just as an aside here, if you're kind of struggling with this, if over here I said this to you, 2 equals 4x times 8, right? So if that was the problem I gave you, you'd kind of look at it like, what? This is just a strange looking problem. But I think what you would ultimately come to is you'd say, well, okay, 4 times 8, I can simplify that, and you would say, all right, 2 equals 32x, and then you just divide by 32, right? Okay, and now that would be the logical way to go about it. Okay, however, there is another way you could do it. So you could not bother to multiply by 4 and 8, and you could just say, you know what, I am going to divide by 4 times 8. That would allow you to cancel your 4. It would allow you to cancel your 8. So x would still be by itself. And then 4 times 8, of course, is 32, which is exactly what you had over here anyway. Right? So you'd still get 1/16 as an answer. So that's all to say, don't let it bother you when there's stuff on both sides of your variable. You can just divide by the product of them. So we end up with the natural log of 2 is equal to 4t natural log 1 plus 0.05 over 4. And I'll just divide by 4 times the natural log of 1 plus 0.05 over 4 on both sides. Those cancel. T is by itself. But of course, this is an application problem. We want to know what the approximation to this is. This might be a good one for us to go ahead and take a look at our calculator on. So I'm going to get out of here, clear this. So typing in what we just discovered, we have the natural log of 2, but again, don't forget about what's in the denominator. So we'll have 12 natural log of 1 plus 0.05 over 4, and then close those parentheses off there. Oh, excuse me, for 12, where did that come from? I was looking at the wrong number. That should be a 4, correct? So 4 natural log of all that. Okay, so we hit enter. 13.95 years, I guess. Okay, so going back here, we can say that t is approximately 13.95 years. Okay, now a good practice to see if you're feeling okay about all this is to do the same thing, but if it compounds monthly, right? If it compounds monthly, what do you get? And I'm not going to do the work for it. I'm just going to give you the answer, but I want you to try to come up with this yourself. You should get something very close to our other answer, 13.89 years. So what is this all about? Well, we're talking about how long does it take for me to double an investment, and we've discussed in the past how compounding more often is a little bit better. So what this is saying is that if you compound your interest monthly instead of quarterly, it's going to take you slightly less time to double your investment than it would if you did it quarterly. But again, it's a very small difference, right? So increasing your compounding only helps so much. Okay, very last example here actually asks us to go back to example 1 from this section, which was actually in a separate video, which we had this function here, a of t is equal to 50 times 1/2 to the t over 13. So this was the amount of iodine, I think it was 123 left after t hours. So we had that function, okay? Now if you think about a decaying substance will be decaying more or less continuously, right? So if we think back to what we learned about continuous compounding, we know that we want to be using this type of an equation, right? Now that's not to say that what I have here, this is still totally accurate. But we like, I should say it this way, we like when we have this kind of continuous exponential growth or decay, we kind of like to have it in this form, a e to the RT. So what we might want to be able to do is to rewrite an equation that's expressed like this in this manner. Okay, so that will allow us to state the continuous decay rate of the substance, okay, which would be our R value. All right, so how do we do this? Okay, well, A is going to be the same no matter what, right? That's going to be 50 for both of them. So what I'm going to do is I'm going to set them equal to each other. So I'm going to start off with 50 times 1/2 to to the t over 13. And then I'm going to say, okay, how do I make that equal to 50 e to the rt? What should r be in order to make these two things perfectly equivalent? So right off the bat, I can get rid of these 50s, right? They're irrelevant. Okay, so we have 1/2 to the t over 13 equals e to the rt. Now I've got these t's here, and I want to solve for r. I'm not really crazy about having these two different variables when I have only one equation, right? So how do I get around this? Well, the answer is, if I think about my exponent laws, I can simplify this equation to where t doesn't have to come into play anymore. And here's how. Right now on this right side, I'm multiplying my r and my t, right? By our exponent laws, we know that that's the same as taking a power raised to a power. And I can play the same game over here. I can say this is 1/2 to the 1/13 raised to the t power. And so if I have something to the t equals a different thing to the t, it must be that this and this are equal. All right, so over here then, I can say 1/2 to the 1/13 equals e to the r. But I'm trying to solve for r, right? Okay, well, it's in the exponent, so let's take the log of both sides, but I think there's a really smart log we can use, which would be the natural log, especially in this case. Why? Because there's an e here. So if I take the natural log of 1/2 to the 1/13 and the natural log of e to the r, then we know that the natural log and the e kind of just zap each other and r goes by itself. But on this, I can bring the 1/13 down, so it becomes 1/13 natural log 1/2. So this is going to be my continuous relative decay rate. All right, so that, and by the way, you also might see it like this. So r equals 1/13 natural log of 1/2. You'll also see it expressed this way, negative 1/13 natural log of 2. And that's done because it's kind of cumbersome to have 1/2 in the exponent. And this is a decay function, right? And the fact that it's a decay function, it's nice if it's really apparent that it should be a decay function. So if I pick the second version here, then it becomes this. And whenever I see a negative up in the exponent, that's definitely making me think of exponential decay. All right, why are these two things equal? What I would remind you of is this: the natural log of 1/2 is the same as the natural log of 2 to the negative 1, which allows you to bring the negative 1 down in front. So that's why the natural log of 1/2 equals the negative natural log of 2. All right, it would not be wrong at all if you put this up in the exponent. That would be totally fine. But I'm kind of partial to this one because it's a little cleaner. So that is this same function, but it's in this form where we get to use e.